Welcome to Breadboarding. This is video 5 in the Breadboard PC series, and in this video we're going to be installing the processor, the CPU, and we're going to be testing it with a very simple test by hardwiring the no operation code. So that basically just allows the CPU to cycle through all the addresses, and we can just check to see that the clock and the control lines are all working properly. So in the previous videos we've covered the high level plan, we've done the reset and power supervisor circuit, the main system clock. If you want to go back and watch the earlier videos, then there will be a playlist for the whole Breadboard PC series at the end of this video. I will include a link at the top of the screen here for the previous video. So let's just have a look at the block diagram just to show our progress. So we've done the 14.3 megahertz clock and the reset and clock circuit. When we plug in the 8088, we're just going to have raw access to the data bus, the address bus, and we'll look at the data sheet in a minute, and we'll see that we won't be able to get a very clear view of the situation here, because until we install the bus controller, buffers and latches, then some of these buses are multiplexed, and at different times in the CPU cycle different information will be on these buses. So it will be a little confusing when we see what's on the logic analyzer, but we should be able to see some sort of progression of the addresses going up through the range. So this is an extract from the PCXT technical reference schematic, and this part here is the clock circuit we've already done. Now the main outputs coming out of the clock circuit into the CPU are these ready, the clock 88 and the reset lines. There are these two lines that we haven't done anything with at the moment, which are related to the direct memory access and wait state. We will need to do something with those, otherwise we won't get the necessary signal coming out on the ready here. There are various other signals we need to worry about on the 8088, the main one being the minimum mode, max mode. So we're running this processor in max mode, which is what the IBM PC did, and we'll cover all of the various signals in the datasheet in a minute. So let's take a look at the 8088 datasheet. So there is a separate datasheet for the 8086. So this is the one with the 8-bit data bus interface, 16-bit internal architecture, and the one we're using is a P8088, which just means it's in a plastic package. The original 8088 I think was in a ceramic package. So got the pin layout here. We'll just have a quick run through those and we'll zoom in. So it's a 40-pin package. Interesting, there's actually two ground signals, and I have read somewhere that both of those grounds need to be tied to ground. There's the voltage, again 5 volt standard, and you can see here we've got the minimum mode and the maximum mode, and we're using the maximum mode, and the way how we select this is with the min max. If max is tied to 0 ground, then we run in maximum mode. When running in maximum mode, then it does require the bus controller, which we'll be looking at in the subsequent videos. So as far as the signals, the AD0 to AD7 is the multiplex data and lower 8 address bus lines. Then the next 8 lines going up to A15 then are permanently allocated, and then the top 4 address lines actually also toggle with various status signals, and we'll look at those a little bit later. And then you can also see that the various signals down here are different depending on which mode we're in. We've got the clock coming in from the clock circuit. That is our 33% duty cycle 4.7 megahertz clock. And there's also the ready and reset signals. Ready is related to memory weight, so we want that to be high generally unless we want to extend bus cycles. And the reset is high to reset. I'm just going to go through this and pick out a few key points. So you can see here the S4 and S3 indicate whether or not the address is related to code, data or stack. Unlikely that we're going to need to look at that. The ready signal, this is related to wait states, and so for the moment we just want to tie that to high, and what we need to do then is to make sure that the 8284 clock controller has the necessary input signals to ensure that ready goes high. Interrupts we're not using for the moment, so we just need to tie those to low. The test input we're not using at the moment, so we can just tie that to high for the moment. Non-maskable interrupt, low. Reset is going to the 8284. Clock comes from the 4.7 megahertz clock. and then the min-max mode needs to be low, so we're in maximum mode. Then these are all of the pin details for minimum mode, so we can skip that. And then for the maximum mode, then the S0, S1, S2, they're the key signals that we're going to be looking at during this video, in that they indicate whether or not it's accessing code or memory, or whether it's not doing anything. Then there's a couple of bus request signals, which I think only the 0 one is used, perhaps when we add DMA, and that will be sometime in the future. Similarly, lock DMA. QS0 and QS1 just gives us some information about the queue pipeline for the processor. Again, we probably don't need to worry about that too much, but we might track those signals just to see what's going on. Then there's some information here. When the processor comes out of reset, then it looks for addresses starting at FFF0 through FFFF. So that would normally include jump instructions to an initialization routine that would set up all the necessary registers and things. And what we're going to be doing in this particular video, we're going to use a no operation instruction. And all that's going to do is, rather than jumping anywhere, what it's going to do is just to get the processor to cycle through the address ranges, so we can just see whether or not it's actually operating. The thing about the 8088 and 8086 cycles, they're known as T1, T2, T3 and T4, so 4 clock cycles. T1 generally is when the address is latched, and when the address latch enable goes low is the point at where latches and things will need to save the values of these things. So when we're looking at Logic Analyzer, we're probably going to see a number of values on the S0 to S2 signals, probably 111, which is nothing much happening, and the other one probably being instruction fetch. I wouldn't expect to see any of these others. So then we've got the power ratings. Now the plastic P8088 maximum current is about 250 milliamps, and so that will give us about 1.25 watts. So if you compare the power dissipation for these processors compared to modern processors, obviously it's probably 10 to 20, 30 times higher for modern processors. And the other key thing, the processors we're dealing with here, they're not static like the CMOS. So on some videos you may see that the use of the CMOS 80C88. Now the CMOS chips are actually static, which means that they don't have a slowest clock signal, whereas you can see here the minimum cycle period is about 5 megahertz and the maximum cycle time is 2 megahertz. So in fact we need to run this between about 5 and 2 megahertz. If we ran it any slower than that, there are some internal, the internal registers and things are kind of refreshed by the clock. So if you run anything slower, like a single button per cycle, then this won't work. But then we get to the instructions. Now the interesting thing is here is we want the no operation instruction, which I happen to know anyway is 90 hexadecimal. And in fact, in the datasheet here, it doesn't actually include the no operation instruction, which was a little surprising. So in all of this stuff, there wasn't processor control would expect to have no operation. So no operation is 10110000, and that's 90 in hexadecimal. So let's switch back to have a look at the XT technical reference. So I've got an extract from the technical reference. This is sort of part of Appendix B, page 449 if you open it in the PDF viewer, and you can see here under processor control it's got no operation 1001, so that's 90 hexadecimal. And what we're going to be doing is just tying the D0 or AD0 to AD7. We'll tie the zeros to ground with a resistor, and we'll tie the ones to 5 volts with a resistor. So let's take a look at the KiCad schematic. So this is a KiCad schematic we were using earlier. And the only thing I have done here different from the previous circuit is that these two signals here previously, so the AEN1 and READY1, were just left ready to tie into the rest of the circuit. But in fact here, to be able to use this, we actually need to tie these to ground and to 5 volts. So then if we look down here, you can see that we've got, these are all the various address lines going off to the latches and multiplexers and buffers, and The AD0 to AD7 is where we're going to be tying these to either ground or 5 volts using a 4.7k resistor. We've got the clock. This is the 4.7 megahertz clock with a 33% duty cycle coming in. We then got the 2 interrupt signals. We're just going to tie those to ground for the moment. We don't want those to interfere with anything. The 2 bus request signals there will just be tied to 5 volts for the moment, so we don't need to worry about those too much. Lock is not actually connected to anything at the moment. That will go off to some of the DMA control logic at some point in time. Test will just tie to 5 volts for the moment. So the 3 main inputs into this will be the ready, the reset, and the clock are coming in from this one up here. And I will just need to redo some of the wiring for connecting the outputs from here and the in here. I wired those up with loose connections. I'll put some better cut cables in there. So we're going to now go in and plug in the processor into the breadboard, and we'll just make a few of these changes, wire up everything, and then we'll have a go at looking at the pins with Logic Analyzer. Okay, so this is the board as we left it last time, and we just need to replace these 2 flying leads with some slightly more permanent ones. So this goes from the low RST output into the reset down there. We'll just get this to come down the inside of the resistor there. Okay, and then this is the strobe down to P clock. So I'll just fit this one in. Okay, and then this one can go over the top of those 2. Okay, just need to plug in the processor. We'll put this, we need a bit more space on this side, on this side. So just going to plug that in there. Okay, so I'm just going to wire in this and tick off against the KiCad diagram as I go through and do it, but I will speed this up and we'll come back once we've got everything wired in. I'll also wire in the Logic Analyzer to all the various signals that we're going to need to track as well, and then we'll come back and we'll start this up and see whether or not we can get anything interesting out of it. Okay, so just checking all the pull-up resistor values that we need to put in there. So those are the power rails. The min-max is low, so that's max mode. So these are some of the pull-up resistors for some of the bus control signals and test. And we put in the 2 interrupts so that those don't cause any trouble. Then we're going to wire in all of the data lines to the 5 volt line and ground for the 1001000, that's 90 hex. Then we're going to put the 2 in there to make sure the ready signal from the clock circuit there comes down. Wire in ready, reset, and the clock. And then we're going to put in the various Logic Analyzer probes and things onto all the address lines, the data lines, and then the control signals as well, so we can monitor the status of the chip as it progresses through the clock cycles. Okay, so we've installed all of the wires, we've tidied up the wires going from up here where we had jumper cables, and now I've plugged in all of the Logic Analyzer signals. We've actually got the resistors on the data lines there, so we've got 90 in hex, which is our no operation code. So I've plugged in the power up there, and if I just switch over to the Logic Analyzer. Okay, so we're going to trigger on the 5 volts when it's powered on, so I'm just going to start the Logic Analyzer, going to power on the circuit. So it's sampling the data, now reading it. Now we'll try and analyze what's going on. Okay, so we can see that down the bottom here, the power comes on around 0. Then we can see the reset is held high until about 400 milliseconds, and then we get quite a lot of activity. And you can see that the address lines, the lower address lines here, seem to be going through sort of a regular counting sequence, so that's good. But the top 4 bits, so this is A16 to A19 sort of starts in the F range and then goes to 0 after a little while. So we'll just have a look and see what's going on there to see what's going on. Now the QS1 and QS0 signals, QS1 when it's 1 means that the instruction queue is 0. And we can see here, this is where reset is, this is where we start to do some processing. So if we add some timing markers here and some pulse counters, so if we look at the distance between reset and the end of QS1 equals 1, and then we look to count how many clocks we've got, so that's 24 channel is the clock, and then choose A markers, that says there's 6 clocks. So from reset going low to when we start to see activity is 6 clock cycles, which is what the datasheet said we'd expect. And if we look at the S0 to S2 values, we've got 4 and 7. 7 means a passive bus, 4 means it's trying to load an instruction, so that's what we'd expect. So then if we look at the address here for the A0 to A15, we've got F0, and if we look at the top 4 bits of the address, then that is F. So in fact it's trying to load the reset, first instruction from the reset area, which is F0. Now because it then loads 90, which is the NOP code in hexadecimal, then it will then just move on to the next address, which is F1, then F2, F3, F4, F5, and it will keep on doing that until it gets to FFFF. And you'll see here that the top address is F and the lower address is 4 Fs, and then when we get to the next one here, it goes over to 0 and then the higher address is 0. Then after this point continues to 0, 0, 1, then I'll count up. Now because we have the multiplex bus here and we haven't got any latches, then we can't separate out the signals. So we can see it goes back to 0, then 1, 2, and carries on counting. So if we go over to here and we get rid of some of the other values here, so we'll see in amongst the 90 signals, we'll see that we've also got this counting all the way up, and that if we scroll down we can see that it's going up through the ranges as we'd expect. So it looks like it's working. The clocks are driving the circuit, the addresses are doing as expected. They will keep going around. I think once it's got to 0, these A16 to A19 will stay on 0 because this will be down to one of the segment address registers, which will go around to 0 and it won't change after that. So basically the lower 16 address lines will keep on cycling, but I don't believe this one will change. And if we look at the high level, we can see that yes, over a period of time, we look at the A15 value, you can see that it's cycling through the whole address range, but that the higher A16 to A19 pretty much stays at 0 apart from a bit of status information appearing here. So it looks like it's all working, so that's good. So we know that the processor is working and the clocks are working, and so we're then in a good shape to then start wiring this into all the bus control logic and wiring in the various latches and buffers that we need to separate out the address from the data signals. Okay, so let's take a look at where we got to and what we're going to be doing next. So this was our block diagram. So in the next video, what we're going to need to do is we've verified that we're seeing values on the data bus, the address bus and the control bus, but at the moment they're all mingled together. And in the next video, what we're going to be doing is adding the bus controller and the buffers and the latches, which means you'll be able to separate those signals out and we should get a much cleaner view of what's going on. So that's the CPU no operation free runs. We've proven that the processor is running and working and is happy with the various clock and control signals. So in the next video, we're going to wire up the bus controller and configure the latches and buffers, and then we should then be able to see a much cleaner set of signals when we look at the address lines and the data lines. If you don't want to miss out on future videos and you're not already subscribed, please subscribe, and if you can hit like as well, it just helps to make the videos available to a wide number of people. Thanks for watching.